Just a few words about the title. Two of the key ingredients in the safety arguments I'll present today are the notion of agency, or like the absence of, in a predictor. So not any kind of AI system, but something that makes probabilistic predictions. And then the other aspect that's very important is, well, it makes predictions about the questions we ask, and it's going to be epistemically cautious, meaning it's not going to be confidently wrong. It's not going to be confident about claims that turn out to be false. At least asymptotically, of course, right? There can be mistakes if the AI doesn't have enough competence. But what we want is really that as capabilities increase because of more data and more compute, that this propensity for being honest and not have any intention in the world increases, and thus the safety with it. So it starts from the um, notion that in order to cause harm other than by mistake, AIs would need both the capability to harm and the intention to harm. And if we don't have, at least if we're not going to be able to stop the capability train, can we do something about intentions? And then as a good computer scientist, I'm asking, oh, what about the extreme case of no intention? Can we disentangle pure understanding of how the world works, like a physical model, from agency that is being able to achieve goals? And um, and that's what I'll tell you about, like the some of the features in less than 20 minutes of the scientist AI that has these goals. But I really want to clearly first preface that even though the scientist AI itself would not be agentic, it would help us deal with agency. And the simplest way is we can use it as a guardrail, as a monitor for untrusted agents, because we could use it to predict the probability of particular kinds of harm that could follow, that could be caused by actions of an untrusted agent. And then, of course, veto these actions when their predicted probabilities exceeds a threshold. So that's all I will say about the application. But of course, it is important from an economic point of view, and impact in the world. Now, let's talk about the scientist AI. So it is not a chatbot. It is making these approximations of Bayesian posterior probabilities. And we're going to presumably use both, I mean, all the tools in the toolbox right now in machine learning. And in particular, that includes system one predictions, like a pure neural net making predictions, but also potentially some layers of code that we write. On top of that, system two reasoning, including reasoning over uh, the truth values, the probabilities of truth values of latent variables that are not things we observe. One of the key and crucial properties of the scientist AI is that the random variables that we're going to be modeling are all indexed by a natural language statement, a sequence of words, right? So that's true for both the latent variables and the observed variables. Um, they live in the same space. It's a space of all the, say, Boolean statements, Boolean variables that can be named using some sequence of words, right? And we're very, very careful here to distinguish the Boolean random variable and the truth value that it has from the words that are used to describe, what is the semantics that we expect from this random variable, and that you can think of that as the index of the random variable. Okay. The other big ingredient, especially for this safety argument, is how we process data. So we're going to use all the same data as everyone else. I mean, whatever we get access to. Um, it's not just scientific data. I mean, some people read scientist AI and they think, oh, it's just going to do science. Well, no. Um, the whole point is to build machines that understand the whole world, not just the scientific data, but human society, uh, harm. Right? What does that mean? And so we're going to, because as I said, the random variables are these Boolean variables that are true or false, the statements. the data isn't like this, right? The raw data is a sequence of tokens. So we're going to transform the sequence of tokens into a sequence of these true statements. Okay, so how do we transform, for example, texts into true statements? Because people say all sorts of things. Well, it's actually very easy. If you have a sentence X and you're not sure whether X is true, but you're sure that somebody wrote it because you picked it up in some website, then you could say someone wrote X. And that becomes the statement that the AI is going to predict. I mean, in the sense, it's going to predict whether it's true or false. If you're sure that X is true because maybe it's a mathematical theorem, or it's the output of a program that was executed, or it's really a scientific fact that has been like an experimental observation you're sure of, then you could just use a different syntax that says X is true. So X, replace whatever is the thing that's supposed to be true or said. But from the point of view of the safety argument, the important point here is not just that we're going to teach the AI about how to trust different kinds of data sources. It will have that as a side effect. But more importantly, we want to make a distinction between properties of the world, like actual properties of the world, and opinions, or what humans would do. Because we want to avoid having no choice when we interrogate, for example, an LLM, to be in a mode of imitating humans, because humans are agents. And the other cool thing about such a transformation, and I just explained like the high level idea of it here, is that it's going to make this syntactic change is going to make every statement true, at least with very high probability, if we trust the pipeline of data collection. Few words again about the probabilistic model. So we can have versions where we only look at the statements in the data, but it's much more interesting to think of the whole thing as a latent variable model, because the data set will only contain so many statements. And what about all the others? Well, we're going to ask the AI to generalize about every other statements that could be expressed in natural language, and that has sort of a reasonable semantics as expressing that something is true or not. And of course, a lot of these variables we are the ones that we want to query, and you can consider them latent. But they are also important to explain the ones that we do observe, right? So if we observe that someone wrote X, then among the latent variables that we should consider to explain that someone wrote X, of course, is whether X is true or not. But we'll never be sure. It's a latent variable. However, we can let the neural net make probabilistic predictions about this, as well as many other random variables that are latent. And in general, the whole thing is going to be trying to produce good explanations for the things it sees. Another advantage of having these kinds of latent variables is that as I mentioned, that there are very few types of data for which we'll be sure that something is true. But for every statement like someone wrote X, we can introduce the latent variable X is true. That means there will be a gradient signal that's going to force the AI to commit at least a probability about whether X is true. Otherwise, we would never see much data about X is true if X is about like people and psychology and society, right? Okay, so I'm gonna first give you a very high level structure of the argument, then I will go into more details. What we want to uh, convince you of is that there's a way to train an AI system, scientist AI or others potentially that have similar properties, that give us these probabilistic predictions that we can trust. And the core safety claim is going to arise from the two high-level properties I mentioned. So we want to show that our defined properties that give rise to a very high confidence that it has no agency, meaning it has no external goals in the outside world, outside of the AI. And the second one is epistemic caution. No, we don't want to see confident but false predictions. For agency, the two supporting claims will be that agency does not arise from how we optimize the system, including how we initialize it. And I'll go back to that, of course. And then it does not arise from imitation, which is an issue with LLMs because they're trained to imitate people. On the epistemic caution side, this will be again supported by two subclaims. One is going to ride on a particular property of truth. If you have sets of statements that are true, that are subsets of other sets of statements that are true, then you can get a notion of generalization that is going to work for us. It's going to mean that we're going to train the system to generalize truthfully, even if we're not sure. If it is not sure, then it should just say don't know or have a probability that is not extreme. And I'll talk about that. And yeah, and then of course the other aspect I already mentioned is the truthification pipeline, which is going to be designed to provide examples of true statements, including the fact that somebody said something or wrote something in a venue, blah blah blah. Right? Okay. A key concept here to be able to make claims about being not agentic is understanding what is agency, and well, different people may have different definitions here, so I'm going to try to explain how I see agency. It wouldn't be a very good definition if any system that causes effects in the world is considered agency, because then every computer program is agentic. So that's not really sufficient. It must push up the expected value of some utility function, and we're going to be taking a kind of worst case scenario for this. We don't know what is the utility function that some bad agent may have. But more importantly, the effect in the world needs to be significant and robust. So what I mean by robust is that the agent is still going to be able to achieve its goals in spite of randomness in the world, unexpected obstacles, and even more significant, the presence of other agents in the world that may oppose those goals. So thinking about all this forces, I think, us to view agency as a graded quantity. Although we might want to say something is agentic if it has a score greater than some threshold, and then I'm going to declare that a score of 0 means totally non-agentic. So agency is something between 0 and whatever. The other property that is sort of a side effect of this notion of agency is that agency requires coordination across multiple actions. So a random mistake is not going to count as agency. And if you, for example, draw weights of a neural net randomly, you're not going to get agency for similar reasons. A key element of the argument, which I guess you're going to have to take on faith, but I think most people will agree, is that the laws of physics, and then by extension, the asymptotic Bayesian posterior is not agentic. The laws of physics don't care about you, don't care about me. They don't have particular goals. So if we have a really good model of the world, which you can think of derived from physics plus computational constraints, yeah, I think we could declare that as the reference for being not agentic. And then, of course, the Bayesian posteriors will converge to a uniform mixture over the possible laws of physics and the possible theories of the world that are consistent with an infinite amount of data. And using like simple assumptions about the form of how we quantify agency, you can conclude that the posterior itself, which is a mixture, a convex combination of these non-agentic models, is not agentic. Okay. Another crucial piece of the argument has to do with how we're going to do the optimization. How are we going to train a system? But there's, the details here maybe don't matter so much as a crucial property that I call myopia. It's a notion that has been, of course, discussed already in AI safety. But the angle I'm going to take here is that the updates that we're going to do to some predictor are invariant to the consequences of the predictions in the world, right? So from the point of view of optimization, the direction in which the optimization is going to go isn't particularly attracted to agentic solutions. And because of the previous slide, we're going to choose a training objective which will converge towards Bayesian posteriors, and in particular, maybe the asymptotic one. The training is both going to start from a non-agentic solution because we initialize randomly, and it's going to converge towards the non-agentic solutions. The question is what happens in between, and what happens in between is there is no drift towards agentic solution because of the way we're going to set it up. So that the updates are consequence invariant. For example, a normal prediction loss will have this property with a neural net and SGD updates. And then if you think a little bit mathematically about this, there are really two forces at play in the trajectories, which are random due to the randomness of many batches and data. There's going to be the randomness, which could make the system more agentic or less. I mean, just randomly. There's no particular drift towards agency, but it's a possibility. But SGD and other optimization methods, or also the updates in the Bayes posterior itself as you collect more data, have contractive properties towards the target, towards some target. And the target is going to be not agentic. So these two forces you can analyze mathematically, and essentially the bottom line is, yes, there's going to be a bit of noise around the trajectory that starts non-agentic, ends non-agentic, and has a bit of oscillations due to randomness, but this contractive force will bring you towards something not agentic. Okay, I think I said these things. Now, what happened? You don't see the figure. I don't see the figure. All right. I'll have to hand wave the figure. So let's think about sets of statements that belong to different categories. So there's the data set, which if we do our job, reasonably well, will be a set of true facts, including facts about what people say, right? And of course, we can grow that data set, and we can call this larger set asymptotically being all the things that the best human science could cook up to create a very big data set of facts, including facts that can be deduced from other facts, like the value of Bayesian posterior probabilities, which is given uniquely, given a data set, the probabilities of particular statements is a deterministic function of the data set, and of course given the prior is fixed. So yeah, so that there's these sets of true statements, and then this is where the data set would converge, which is what machine learning is usually interested in. In theory, it could converge to a larger set, which would be things that, say, if we have like super intelligence, maybe the AI ends up being able to conclude things that us, the humans who prepare a data set, might not be able to conclude because it has better algorithms. And so, yeah, it is possible that the AI would generalize there, but we're not sure. It could just decide to generalize to the things that humans would be able to say is true. And that's interesting. I mean, so that means we're not solving the elk challenge, for those who know about it. We have no guarantees of where this generalization, how far it will go, but we know that at least it will converge to the set of things that humans would consider true, for sure, right? So we're not talking about beliefs of humans like scientific theories. We're talking about facts. A fact might be that a theory is dominant or succeeds in explaining everything. But all right. I think this is the last slide, and I'm already close to end. But it shows a bit of the structure of the safety argument. So I've already done kind of the top of this. We have like, okay, the scientist AI is safe because it has no agency, it has no, it has epistemic caution, and no agency comes from the fact that it's the optimization process to train it is not going to yield agency. And once it's trained, we don't use it to imitate people. Because of course, if you had a very good predictor, you can just ask it about the probability that an agent would do some action in order to achieve some goal, and then you could just follow those actions, and you would have a good agent, right? But this would be under our control. It's not something that would happen behind our back. And if we absolutely want to be sure to have no agency, we can just make sure that doesn't happen. Um, I kind of explained the high level story about optimization. Um, some of the assumptions, that I didn't mention, like, of course, we have to be careful how the data set is constructed. If an adversary constructed a data set of false facts, then, of course, it could make the scientist AI start making predictions in any weird direction that could be bad. Um, uh, there are some conditions, technical conditions, to make sure, for example, that the Bayesian posterior is unique, and but they are not very difficult. There are also some conditions discussed in the paper that is in preparation that has to do with the fact that there's enough data for the AI to learn the semantics of language and the composition structure of a language. And okay, so I'll stop here and take questions.